Okay, Year 12. So today we'll look at the coefficient of determination and the next exercise, which I can't remember at this stage. But before we go into the r squared value, let's go back and just finish off one little thing we didn't do from the last lesson. So it was these three plots. Now, remember that if we are using Pearson's correlation coefficient, or the r value, which is that number between -1 and 1, it does assume that the data, so these are the assumptions when we use Pearson, that there is a linear association. So the dots need to form a rough straight line. Okay, now it doesn't have to be perfect, remember, it can be roughly straight. It has to also, so it assumes no outliers, because outliers have a massive impact on the R value. Now if you look at this data here, which is, you imagine a line of best fit drawn on this, and where are you? Come on, this one. So I'm just going to draw a rough line of best fit through there, and you can see that we've got this one dot that just doesn't conform to the overall pattern. And we can see that if we actually include this outlier in the calculation of Pearson's correlation coefficient, the R value is 0.5. And going back to these diagrams here, 0.5 is on the cusp, or on the border between weak and moderate. Okay, it officially would be classified as moderate, I think. Yeah, moderate. Okay, but if you look at this, it looks really good, like there is a real clear-cut correlation. And actually, if you don't include this outlier, if you remove it from the data set and recalculate it, we can see that the R value in fact is 0.77, which is much higher. I think it's strong positive. Yeah, strong positive. So yeah, like it's important to note that, okay? And then, like, basically if you were doing research and this was your data set, you would actually sort of seriously consider this data point and actually try to work out whether you include it or exclude it from the data set, because whatever we're investigating here, this EV and RV, it's worth proceeding with the investigation if we see a pattern like this, even though the R value is only 0.5. One final thing then to look at from the previous exercise: is there an outlier in the following scatter plot? So here's the scatter plot here, and we've got this data point here, 60, 60. Now, is this an outlier? Well, you look at it and we often think about an outlier as something that just is sitting there by itself, and it does certainly look like it. But if we imagine a line of best fit, again drawn on this data, a line through there, right, this dot really does conform to the line of best fit. So actually this is not an unusual value. As the EV increases here, we're expecting the response variable to behave like this, and this is really conforming to what we would expect. So is there an outlier in the following scatter plot? No. So to be an outlier, it has to deviate from the linear pattern. This is bang on the linear pattern, so therefore it is not an outlier. Alright, on to today's work. Alrighty, so calculating R. So this is the coefficient of determination. So I'll just go back and we'll quickly do these again. So I'm going to go add lists and spreadsheets. So type that in. For the weights and the heights are the following. Alright, so what I'll do is go Control Doc and Data and Statistics. Alright, we're going to grab the weight, the height rather. That explains the weight. Alright, so there's our scatter plot. Now let's go back to, so I'm going to go Control and back to this here, and I'm actually going to perform linear regression. So remember, we go menu, 4, 1, and 4. Alright, our x is the explanatory, that's our weight, which explains the height. And throw it in C. Now, in this last lesson, we were looking for this r value here. Now, we can also pull out the r squared value from this, or we can simply grab the r value ourselves, this one here, and square it and actually find it ourselves. So there's two ways of doing it. We can get the calculator to do it for us, but if we have an r value, we can simply square it and we get the r squared value. All right. So what the r squared value does, so the coefficient of determination, that's r squared, is the degree to which one variable can be predicted from another linearly related variable. Okay. Now, here's how it works. So we've got carbon monoxide levels in the air and volume of traffic are linearly related with a correlation coefficient value of r of 0.985. So basically, if you imagine it, as the amount of traffic increases, so too does the level of carbon monoxide. That makes sense. More cars on the road, emitting more smoke, etc. So we know that it's got an r value of this. So we're going to determine the value of the coefficient of determination, write it as a percentage, and interpret how the volume of traffic impacts the carbon monoxide CO levels. So when we convert it to a percentage, let's just say that that is going to be to 2 decimal places. VCAR or a SAC will tell you exactly how many decimal places. Right, so to do it, I'm going to go to Control Doc to grab a calculator, and I'm going to type in brackets 0.985, and I'm going to square it. Okay, so I'm going to write down 0.985 in brackets squared equals 0.970225. Now, so that's the r squared value. So r squared equals the r value squared, which is this value here. We want to write it as a percentage to 2 decimal places. So what I would do is on the calculator, multiply this over here, multiply this by 100. So it's going to be 97.02%. All right, and we're now going to do the interpretation. Now, this is a script that you need to follow. I believe you know this script from last year. So what we're going to say here is the r squared value, so it's this. So we're going to say that 97.02% of variation in, all right, and we're talking about variation in the response variable here. All right, now the response variable in this case is carbon monoxide levels. So 97.02% of variation in carbon monoxide levels can be explained by, and here's what we do, we put the explanatory variable in here, which is, can be explained by volume of traffic. Alright, so lots of the variation in carbon monoxide levels can be explained by volume in traffic. In fact, that there's 3% of other things. I don't know, that might be other things like methane in the air and stuff like that. I don't know, just other stuff. But lots of things are explained by variation in carbon monoxide. Alright, so that's the basic script. So I'm just going to highlight the things that you would change depending on the case. So the first thing I'm going to highlight is the r squared value. Alright, so that will be whatever the r squared value as a percentage is. Variation in, so this next one is also going to change. This is going to change to whatever the RV is. Alright, and this one here is going to change to whatever the EV is. All right, so all you do to answer these questions here is you simply write your R squared percentage here, your RV here, and your EV here. Can't go wrong. All right, let's try it on another one. Data scores on tests, the influence of... bit of a typo there. Anyway, what we're doing is we're comparing or looking at the influence of verbal ability on mathematical ability. And what we're saying is that they have a correlation coefficient of R equals negative 0.275. Okay, so what we're doing is the influence of verbal. Okay, so verbal is here and mathematical ability is there. So we're seeing how mathematical ability responds or is influenced by verbal ability. And it's suggesting that it has this R value here. Okay, so it's negative, which means that it would go in this direction here, but it's a pretty weak R value. Okay, so that's really low. In fact, it's suggesting pretty much no correlation between the two things. Anyway, it doesn't matter. What they want us to do is determine the value of the coefficient of determination, write its percentage, and interpret. And mathematical ability is the RV. Oh yeah, we've got that down. Alright, so what we're going to do is just like last time, write down R squared equals negative 0.275 squared equals. So we're going to go to our calculator, and I'm just going to show you something about brackets here and why I've been bracketing this. So if I put down negative 0.275 all squared, what it does is the calculator doesn't know that you want all of the negatives squared as well, and so it gives you this negative answer here. So what we want to do is make sure that we bracket, put down negative 0.275, square it, and hit enter, and we get that number there. So it's 0.075625. Now we're going to multiply that by 100, which is 7.56, assuming it's 2 decimal places, percent. Alright, so that's our percentage. So we're going to use the same script as before, and we're going to say that 7.56% of variation in... Now, remember what we do is we put our, what is it? The EV or the RV. So you go up and have a look at your notes. It's the RV that gets mentioned here. So the RV is mathematical ability. I don't know whether you can hear my dog actually snoring there, but yeah, he's going for it underneath the desk. Variation in mathematical ability can be explained by verbal ability. In other words, hardly any of the variation in mathematical ability is explained by verbal ability. It's something else. There's something else going on. Who your primary school teacher was, I don't know, all sorts of things. Alright, the final question here, for the relationship described by this scatter plot here, the coefficient of determination, R squared, is this, and they want us to work out the value of the correlation coefficient. Let's just say this time the specification was to 3 decimal places. So let's do it to 3. Alrighty, so to do this, what we need to do is we need to square root this value here to get back to the R. Right, so we're going to square root it. But we're also going to note that this graph here goes like that, which means that the R value has to be negative. Alright, so what I'm going to do is square root this. So R equals the square root of this value here, 0.5210, and I'm going to shove the negative sign out the front because it's got to have a negative R value. This is a really common type of question. So R equals. Right, so we go to the calculator and I'm going to go control that with a negative sign out the front, 0.5210 means I've got negative 0.27222 to 3 decimal places. So that's our R value. And again, we can check this in vice versa by saying that if I bracket that and square that, it should take me back to my original R squared value. So if I hit enter, here it is, 521, 521. All right, so the work is there. Okay, and let's just roll straight on to correlation and causality. So this is a bit of a kind of like a wordy exercise, not really a mathematical exercise. So I'll just talk you through it. A statistical correlation may be found between two variables. However, that does not mean that one variable causes a particular result in the other. So we want to really be careful about using this word, one thing cause. In fact, the suggestion is that you should not use that word, or like proves, okay, in statistics. So proves or causes, they're dangerous words in statistics. So some other factors may be involved. So here's an example. A strong positive correlation is found between public holidays and traffic accidents. Does this mean that public holidays cause accidents? What other likely factors are, or what other factors are likely to be involved? So here you've got things like, so when people have public holidays, they might be out, which means alcohol might be a factor. They might have had a big night the night before. They might be tired, okay? They might not be concentrating. They might be driving on unusual roads. There's all sorts of other things going on. So even though we've got this correlation between public holidays and traffic accidents, we can't really say that public holidays cause traffic accidents, okay? So non-causal explanations for an association. So there are 4 possible explanations for an association between the two variables. One is causation. So one variable is actually causing a change in the other variable. And this is a factor here. So the taller you get, the more you're going to weigh. So that's weight and height. Okay, it's a fact. The more of you there is, the more you weigh. So height causes a change in weight. All right, but we can have this thing called common response. So some other factor is causing both variables to change. So we've got a strong positive correlation between the number of people using sunscreen and the number of people fainting. Okay, so here you'd be like, oh yeah, this is something here. But actually what they're doing is both of these variables, people fainting and the number of people using sunscreen, are both responding to a third variable, and that is the temperature. Now what happens is, as the temperature increases, people tend to use sunscreen. As the temperature increases, people tend to faint. So both variables are associated because they are strongly associated with this third variable. Okay, and this is called the common response. So sunscreen, okay, doesn't cause fainting. Okay, the variables are associated, but in fact both of them are responding to a third variable, which is temperature. So this is what we call the common response. All right, we can have this thing called a confounding variable. So it's unclear how the variables are related, and we are not able to draw conclusions about causation or common response. So there may be an unknown factor involved, which is called a confounding variable. So crime rates and unemployment rates are strongly associated. That is, the higher the unemployment rate, the more people commit crime. So does a decrease in unemployment cause rates to decrease in crime rates? Maybe, maybe not. The state of economy should be considered. So is that a factor? Unemployment rates cause crime rates, or does the state of economy cause the crime rates? These are questions here that we just don't know the answer to. So there's a confounding variable in here. All right, another one is coincidence, and the association between two variables is occurring completely by chance. So it's impossible to identify any feasible confounding variables to explain a particular association. For example, the consumption of peanut butter and marriage rates. That is, the more peanut butter is consumed, the higher the marriage rate. Can we conclude that people who eat peanut butter will get married? Eating peanut butter causes people to marry? Absolutely not. The two variables are completely associated by chance. All right, so here's a question from a paper in the past. Scatterplot shows the TV sets and the number of doctors, and we can see here that as the number of doctors increases, so too does TV sets per 1,000 people. So a politician, upon seeing a graph similar to this, suggested that his country should provide more TV sets to increase the number of doctors in the community. Okay, but a more correct interpretation of the data is this is just purely a coincidence that the two things are associated. They got nothing to do with each other. All right, so try that out on 3H and use these kind of 4 things here to try and see what's going on in those questions.